All right, so we are going to look at yet another uniform circular motion problem. In this case, we are going to talk about a car making a turn and the amount of friction that a wheel will have when a car makes that kind of turn. So let's start off by first drawing a top-down view. Let me bring this all the way down. So imagine that I have my road like so, and I have a car that is making that turn around that road. Now, when dealing with a problem like this, it's important that we talk about some of the forces that are acting on the system. So let's talk about that. So I'm going to have my car. Here's my car. Okay. And the forces that are acting on that car. Well, first of all, I have the force of gravity, mg. I have the force normal, or the force reactionary, that is upwards. And then lastly, there is a force of friction that is forcing the car to make the curve. Now, if you don't believe me, think about driving this car in the ice or on the snow. What you experience when there's too much ice or too much snow and you don't have enough traction, your car just skids off the road. It just slides off the road. So it is the friction that is forcing the car to make that turn. So we have a force of friction in that direction. Okay? Now let's talk about the force of friction in this way, and more specifically, let's think about it as the force static friction, because the wheel themselves are not moving in the direction of that force. They're moving in this direction. So we can imagine that it's the static friction that's keeping the tire in place. And not to mention the rolling motion of the tire also isn't kinetic friction, because the areas aren't moving with respect to each other. They're just simply falling on top of each other. So static friction is what we're going to talk about, and we are going to set the coefficient of static friction to be about 0.5 in this problem. Okay? So those are the things we're going to deal with. I can immediately calculate my force of friction. I'm going to move that up there so I can calculate my force of friction. That way we can keep looking at it. We need it. Okay, so the force of friction, which is my center pointing force here, my force of friction is equal to my normal times my coefficient. And because of the diagram I have up above, I can see that my normal and my weight are going to be the same thing. It's a flat surface. Okay? So that means that my normal is also equal to mg. So that means that my force of friction is equal to mg, my substitution for n, times the coefficient of static. That is my force of friction. That is what's causing an object to move in a circular path. And because of that, I know that this force of friction is also centripetal, meaning that it's making it move in a circular path. Okay? So I can set that equal to the centripetal force equation, which is mass times velocity squared over the radius of curvature. Okay. Quickly, I can look right now and see that this and this can go away. My masses are represented on both sides. So I'm left with G mu static is equal to V squared over R. Now, if I'm trying to calculate the velocity that this car could go through, I'm going to need to make a turn radius. Or if vice versa, if I had the velocity, let's say 20 meters per second, then I can then solve for what is the sharpest turn it can make while still holding traction. What I'm going to do for this problem is I'm going to give it a turn radius. So let's imagine from the center of this car, back here, center of the car to the center of that circle is 20 meters. Okay? So with that being 20 meters, I now have a radius that's equal to 20 meters. And now I'm basically in the end game. I'm about ready just to plug my numbers in and then solve. So let's do that. So first, g, my acceleration due to gravity, it's about 10. We know it's 9.8. But for simplicity's sake, we're going to say it's about 10. We have the coefficient of friction, which I determined previously to be 0.5. Okay, that's equal to v squared over r, which is, in this case, 20 meters. Cool. I move the 20 over to the other side. I've got 20 times 10 times 0.5 is equal to v squared. And I'm going to do this really quickly. Half of 20 is 10, so I'm left with 10 times 10 is equal to v squared, or 10 is equal to v, which means that in this curve of 20 meters radius, that a car can travel no faster than 10 meters per second without losing traction on the road. It can obviously travel slower than that, but no faster than that.